Hello. In this video, we are going to discuss about the mechanical properties of solids, in which we are going to discuss about matter and its types. Further, we are going to discuss about solids, various types such as crystalline, amorphous, and various other things associated with them. Then finally, we'll be dealing with elasticity and the coefficients of elasticity and Hooke's law and the relations that are involved in between them. To start with, what we must first consider is matter. Well, matter, as we know, anything that has mass and that is occupying some space, and that space is filled with molecules, and these molecules, and based on these molecular arrangement, based on the arrangement of molecules, the matter is further divided into solids, the liquid, and gaseous state. Of course, as we know, in solid, the molecules are tightly packed, and in liquid, they are loosely packed, and in gases, well, the packing is almost negligibly packed. So this leads, but we are dealing with solids, so this leads us to know that how solids can be further categorized. Now, the solids are further categorized into the crystalline and the amorphous types. Now, the crystalline solids, or the crystalline structure, tells that it has a sharp melting point, which means that it will melt at a particular temperature. But there is this amorphous kind of solid, it does not have, or they do not have a sharp melting point. The crystalline solids, they are anisotropic in nature, which means that they are the physical properties that they possess, they are different in different directions, which means that the thermal conductivity, uh, take for example the case of thermal conductivity. Now, as you are considering the thermal conductivity of a wire, the wire, as you know, may have the length of the wire is usually considered, so it is a longitudinal shape that we consider, and the cross section is not comparable to the length of a given wire. That is how we construct a wire. So in that case, the thermal conductivity is considered across the length of the wire, but if it is considered across the area of cross section, that is sideways, then it will be different in case of a crystalline solid, whereas in case of an amorphous solid, it is isotropic in nature. That means all the physical properties that we may consider, such as thermal conductivity, the electrical conductivity, or even the refractive index, In case of the optical medium, the properties remain the same in all possible directions. So that is how we differentiate between the crystalline and the amorphous solids. Now let us discuss the nature of the interatomic forces. Now the atom comprises of a nucleus at its center, and it is then surrounded by electrons. So let's assume a nucleus over here, and it is then surrounded by electrons. Now the electrons usually are not like this one by one structure. They are actually in the form of clouds. They cloud around the atom, around the nucleus, sorry. So this is more or less an electron cloud. Now the atoms are electrically neutral, but still you can have these interatomic forces, that is the force between these atoms, and it is electrical in nature as well. That means if you have one atom over here and there's another atom over here with the nucleus and surrounded by the electron cloud. Let me take another ink for this electron cloud that we have at hand. So these two electron clouds, they won't be a problem. The electrons of this atom may be attracted by the nucleus of the other atom, and there will be attraction, so it may attract. But as the electrons or as the atoms, they tend to approach one another, they will stop at a point when the electrons, the electron clouds of one of the atoms is at a very close proximity to the electron cloud of the other atom, say about at a distance of say 5 times of 10 to the power minus 10 meters, which is 5 angstrom. Nearly at 5 angstrom, what happens is that the electrons, they start interacting with one another and they repel each other, start repelling. And as a result of this repulsion, what we find is that we find the various we can study the nature, the orientation of the charges and everything that comes into play. That is what we are about to do. Now take the example over here in this figure that I have made for you. This is the first kind that I'm making. We'll be assuming further cases as well. So here we have the electron clouds that are surrounding the positive charge of two atoms. So this is the first atom and this is the second atom, suppose, and we have the nucleus having the positive charge at the center of each of those atoms. They may be of the same kind for a given molecule, and then we have the electron clouds that are surrounding them with those strips that I have made. Now the two distances that you can see over there, we have R1 to be the distance between the positive charge and the negative electron cloud. Similarly, here also we have considered R1 to be the distance between the positive charge and the negative electron cloud of the other. Now this is the distance resulting in attraction between the two atoms. We haven't considered the distance for the positive charge of the given atom and its own electron cloud, because that attractive force that is present for the atom on its own is responsible for providing the centripetal force for the electrons which revolve about the nucleus of their respective atoms. So that distance has not been considered. Here we are considering the distance between the neighboring atoms. So that provides R1 is the distance which provides the attractive force. R1 for attraction or attractive force. And R2 is the distance, as you can see, between two positive charge, and that provides the maximum repulsive force, distance for repulsive force. The electrons, well, in case of hydrogen also we can find that the electron, there's just one electron. So in that case the electron, the force between force of repulsion between the electron may not be that effective. So we have neglected that. We have considered only the nuclear force of repulsion. And in that case, suppose the attraction now is obviously greater than the repulsion, because as you can see R1 is less than R2 in this case when the atoms are at a certain considerable distance from one another. Now as the electrons are attracted and the clouds come up, there's an overlapping that takes place. Now remember, the electrons are not touching each other, it's the cloud of the electrons that are overlapping. So we can consider that. So now these electrons, they have overlapped, the clouds of the electrons have overlapped as a result of the attractive force. This in turn results in such a type of structure where you have two nuclei and the clouds are somehow arranged like this. Which is a common cloud that is developed surrounding the two nuclei of the two, and therefore now the only force that can be possible is the nuclear repulsive force that is occurring between the two nuclei, and so they cannot move closer any further. So considering the energy in this case, if we observe the potential energy, the potential energy which is a function of distance, of course, this potential energy will be negative in this case, because the for that entire system that we see over there, because the atom, one of the atoms, as it is brought closer to the other atom, so one of the atoms is actually applying some force in that case to attract the other atom. So the work is done by the system itself, and so the work here that we observe is negative, and the work done here is, although that is taken as positive, but the energy term in that case will be negative. And that is by calculation of electrostatic potential energy that we can obtain it to be negative, but that's a separate topic. But as they have been brought closer to one another, this potential energy term that we will be getting over here, that will be positive now, because the work will be done upon the system to get them together or get them closer to one another. So as a result of that, and as you know that potential energy is a function of distance, in this case the positions of the atoms involved, so we can consider the plotting of the potential energy with respect to the distance. as follows. So this is the distance r, which is varying, and we have the positive part and the negative part of the potential energy. And as we consider the variation, it's somewhat like this. It's a pretty familiar graph that you will come across in most of the cases as we will be dealing with various other various other topics. Now, this is the lowest part of the energy, that is at the point P that I have considered, and the this lowest value that is possible, if you remember the value I had just discussed, that is 5 angstrom units distance, and that distance supposedly is termed as r0 or r naught. There, near about those that point, we have the points P1 and P2, which we'll be discussing now. Now the potential energy becomes minimum at that distance, that is 5 angstrom units. After this distance, the repulsive forces come into play because the distances are less, you know. So the repulsive forces come into play, either in case of the repulsive forces between the electrons, or in case of the repulsive forces between the nuclei of the atoms. Uh, the distance at which the atom can coexist with each other is that distance that I have put in over there, that is OA, that is that distance, that is 5 angstrom, where the potential energy is obviously minimum, and the energy tends to exist in the lowest possible state that you can see, that is the value of energy is the maximum negative over there. If the atom possesses some kinetic energy, it will oscillate around its mean position in those limits of P2 and P1. It will tend to oscillate within that in case it has some potential energy, and it does, because the atoms are always under some amount of vibration, because there is some internal energy involved in those atoms. Or conversely, the vibration results in the internal energy of the structure, and that is because the molecular motion never ceases until it reaches the absolute zero. The equation for potential energy curve is found to be U is equal to kx squared, where x is the displacement from the mean position, displacement from the mean position for a given atom. And since the atomic forces are conservative in nature, we can say that F is equal to minus du divided by dx, and that will give me a result of we put that over there and we get minus of kx, where minus of actually it's 2kx because it is x squared over there. So this equation represents a simple harmonic motion. As you can see, that the force is proportional to the negative of the displacement. So this represents an SHM, simple harmonic motion. So it's quite obvious that the atom possessing the energy that we have discussed from the curve, it will oscillate about those points, about that amplitude from its mean position. Now, what's interesting is that had this property, that the interatomic forces and the repulsive forces, the interacting forces being repulsive, had not been there in the close range, then all the molecules, they would have been drawn to a certain single point, reducing the size of the body to a point mass, and then we wouldn't have had a definite or finite size of any body. So it is this repulsive nature that exists, this particular thing that we have a limit on, which is proved by this variation, is what gives bodies their definite size, and to some extent the shape of the bodies as well. Now, just like the case of the interatomic forces, we can have intermolecular forces as well. So we can consider intermolecular forces. And these intermolecular forces have the same uh, properties as that of the interatomic forces, just the difference being that the molecules are composed of atoms. Even though atoms can be having those spherical shapes, but the shape of the molecule really depends on the orientation of atoms present in them, and therefore that determines that determines the force that can exist, the orientation of the uh, molecule, that is due to the atomic structure in it. And it is much weaker than the atomic interatomic forces. The intermolecular forces are much weaker by a scale of 100, say between 50 to 100. And two molecules are in minimum energy state at comparatively larger separation than in case of two atoms, where we find this kind of an approach, or this kind of point P. The separation, however, is larger for that minimum energy condition. And the attraction between two molecules is not limited to just two neighboring molecules. Instead, they have a range which is known as the molecular range, and within that range, anything, the sphere thus constructed with that range as the radius constitutes the sphere of influence of the molecules. We will be dealing with them uh, in the upcoming videos that we have lined up for the intermolecular forces later on, but that is a separate topic of discussion. We'll be continuing with this topic further, but that will be in the next video. Till then, thank you for watching.